All right, hi guys. Let's just get right to it. Get through this stuff fast. We are going to talk about section 5.4 of our Unit 5 kinetics. So what we've talked about so far is we've talked about rates of reaction, how fast they go, several factors that can affect those rates of reaction, and then we've also talked a little bit about some of the equations there, how to come up with the reaction orders, experimentally derived reaction orders, and then we've talked about how to come up with the rate laws for our reactions. Now, what we really haven't talked about is how reactions actually occur. Right? We have two chemicals, they're forming a new chemical. Does it actually happen that easily? And that's what we're going to talk about in a lot of the rest of Unit 5. Okay? So in 5.4, it's called elementary reactions. So an elementary reaction is, what it's talking about is a single step of a reaction. So what we're talking about here is that I have an overall reaction, right? This plus this is going to make this. Well, if it doesn't actually happen in one step, we can break it into individual steps. So this is going to react with this piece, and then they're going to make this new thing that's going to react with this other piece, and then those two things react, and it makes the final end. Okay. And so each step of a reaction, when we break it into individual pieces of what has to react before another piece can react, is called an elementary step. Okay. So in bold here, elementary reactions are a series of simple reactions that represent the progress of the overall reaction. Okay. So each step is usually very simple. Usually only two things are involved, only two molecules that are going to collide and interact with each other. They will make one or two new things, and then those will react in a certain way to make something else. Now, our reactions are not limited to taking place in one single step or two single steps. Sometimes mechanisms in these reactions actually can get really complicated, and we can have a whole lot of steps to them. In this class, most of the time, we kind of cap out at about 3 steps to a reaction. Okay? So, let's see what this kind of looks like here. Keep moving my face around. Okay. Now, I used this term just a second ago, but all of these steps added together, that's kind of like showing how the reaction is going to take place, is called a mechanism. We're actually showing the mechanics behind the reaction taking place. All right? So I kind of have this particulate diagram model of a reaction. Okay, this is essentially we're going to add an acidic ion to this thing is already, this is formic acid. It's a weak acid. Okay, so if I was to actually look at this reaction and write it how we would normally write a chemical reaction, I would take this first step, and then I would just draw one arrow, and then I have the final step. Reactants to products. Okay. Now, this whole point of the reaction mechanism in these elementary steps is that the actual reaction doesn't happen that easily or that quickly or in one step. So a mechanism shows us exactly what's going to happen. Okay, so this acidic H plus proton forms and bonds onto here. We now have this formic acid ion here. And now that breaks apart into water and this cation. And then that cation even breaks apart. Okay. So we end up having multiple steps to that reaction here. Normally when we write it out, we don't show it with particulate models. We can, but we see it as steps written out like this. So it says step 1, that formic acid plus that proton makes this, whatever this is called, formic acid cation. Okay. We also are told a speed over off to the side. That is going to be critical to us in the next slide or two. Okay. Right now, I mean, essentially what you're going to get into is the slow step is the only step that matters. Okay. So hold on to that. And then this ion is going to break apart into these, and then this ion is going to break apart into these. And so that's the individual steps. Now, from those individual steps, we're going to have to be able to put all this together to come up with the overall reaction, the rate laws of the reaction, to determine these things called intermediates and these things called catalysts. So let's introduce some of those other terms here, okay? Now, where should I go? There we go. So we still have those same pieces here. Okay? It says the overall reaction, that proton is consumed in step 1, and notice it is reformed in step 3. I consume it here, and then the reaction kind of poops it back out and makes it all over again. So did I actually consume an H plus in here? Well, if you actually wrote the balanced equation, that H plus wouldn't show up in it because it's both a reactant and a product. Wouldn't that cancel out? But without that H plus, the reaction couldn't have happened. Okay. This is the last topic in Unit 5, as we'll get much more involved with these catalysts. Okay. But so a catalyst, what you need to know is it's used in a step. It doesn't have to be the first step. It could be the second step. It could be the third step, okay? But it's used in a step, and then it's reformed, it's made again in a later step. So it looks like, on an overall basis, it's not actually used. Okay? You're going to have to be able to identify those. And then this also says species such as this formic ion and whatever this ion is that are not reactants or products. And I know this because I look. Step 1, it makes this cation. Step 2 then uses that cation and it decomposes. So again, if I were to combine all of these steps and write all of the reactants on one side and all of the products on the other side, that HCOOH2 plus would cancel out because it's on both sides. Okay? So if it is formed in one step, it's a product in one step, but then it is a reactant in another step, that is called an intermediate. It was intermediately formed and then it was consumed. Okay? So those also don't show up in the overall reactions. Okay, so here's a different reaction here. Here's a mechanism for that reaction. We can then be asked, what is the overall reaction? Combine all of these. We can then be asked to identify any catalysts, and we can be asked to identify the intermediates. Okay, so I hope this kind of shows up. I kind of did it on a piece of paper here because I don't have my whiteboard. But I did on a piece of paper. Hopefully it's not like in reverse order for you guys, okay? So I wrote those 3 steps out. Okay? And then I went through and I tried to see some things. Did I make anything in this first step that I then use as a reactant in step 2 or 3? And yeah, that HOCl was then reused in step 2. So I crossed that out. That would be an intermediate. This OH minus, that hydroxide ion, is consumed in step 3. That would be another intermediate. Okay. Step 2 produces HOBr. Step 3 uses HOBr. Another intermediate. All right? So I cross all those out. And then I also noticed H2O was consumed up here. It was a reactant. And then in the final step, and again, it doesn't have to be the final step. It just has to be on the product side somewhere. It was remade. So that would be a catalyst. Okay. And now I didn't cross that out, I just underlined it. Okay. Because when I combine these into an overall reaction, I grab everything from every single one of those steps on the left side of the arrow. Those are all of my reactants. I then grab anything that's left from the right side of the arrow. Those are all my products. And I rewrite that. Okay. Notice I did not include the catalyst in the reaction. One place that you often will see a catalyst shown, and it doesn't have to be shown there, but it sometimes will, is above the arrow. Okay. which means if you see anything above the arrow, that's a catalyst. That thing has to be present in order for the reaction to occur. Okay? But it's not really a reactant because we remake it at the end. Okay? So, this is all the stuff that you're going to have to be able to do. Perfect. Now, we talked about these this speed over here on the right side. It's usually shown on the right side, okay? Sometimes it might be shown on the left, okay? Don't freak out. But it's either going to be slow or fast. I don't know if I've seen another one, okay? Slow or fast. Now, the thing here is we're talking about kinetics, how fast a reaction happens. And what we end up seeing here is that any step that is labeled slow, we call it the rate determining step, which means how fast that reaction happens is only dependent on how fast the slow step happens. The fast steps happen so fast, it doesn't matter. They happen so fast that the reaction is not like held up by those. The slow step is so slow that in comparison to the fast steps, it's what controls the entire rate of that reaction. Okay? So you are always looking for the slow step. That's the key here. Now, so we're given this reaction here. This is the same one that we were working on a couple slides ago. And it says here we can determine a rate law for this reaction. Now remember, rate laws are only found experimentally. Okay? So we ran some experiments and we actually found this rate law for this reaction. Okay? Now notice, if you actually added up and came up with the overall reaction here, this H plus would not show up because it's a catalyst. But it does show up in the rate law. Okay. Now also notice the coefficients from the slow step here are the same as the coefficients of the reaction orders, 1 and 1. So it's a first order for the formic, it's a first order for the proton. Remember when I said that if the coefficients and the reaction orders are the same, that is a happy coincidence? Well, it's no longer a happy coincidence. All right? What we're now saying here is the slow step, the stoichiometry of the slow step, which means the coefficients, will be the same as the reaction order. Okay. Now, let's talk about this first one right here. It says if the first step is slow, if the first step is slow, your life gets easy. So you like slow first steps. So it says if the first step is slow, then the overall rate for the reaction, the overall rate law, is only based on that slow step. So we do not care what happens in those fast steps. Well, we care. We have to make sure it forms the same things, right? But in terms of the rate, they go so fast that the actual rate isn't determined by them, so we can ignore them. So now I only look at this top one here. A plus A makes B. Well, if I look at this, A plus A makes B is the same thing as saying 2A makes B. Now, here's this key thing. Okay? You can use coefficients from elementary steps. That's the key here. Coefficients from elementary steps, not the overall. You can use coefficients from the elementary steps as your reaction orders. So 2A becomes a second order reaction with respect to A. And since that is the only reactant in the slow step, the overall rate law is just rate equals K times the concentration of A squared. Okay. So slow first steps are fantastic. We love them. Okay. Now this says if a subsequent elementary reaction is slow, then what we're going to have to do is we have to add up all the reactants that get us to that step, cancel any intermediates out, and then now what's left over gives us the actual rate of reaction. Okay, so this one, same mechanism here. It's just the second step is now slow. Okay, well if I look at that, B is an intermediate, so B would cancel out, and what I would be left with, okay, is 2A plus C makes D. All right, I kind of circled them to show you. Those are my new reactants from the elementary steps. And because they're from elementary steps, I can use their coefficients. So the rate law then would be rate equals K times concentration of A squared times concentration of C. Coefficients become the reaction orders. Okay. So you cancel out your intermediates, and what you're left with is your reaction. Okay. Now, what we're not going to get into right now is what happens if not all of your intermediates cancel out in previous fast steps. We'll deal with that later, okay? That's topic like 5.9. Okay, so here's another thing that you're going to have to do. This says you're going to have to actually propose reaction mechanisms. And most of the time, this is not you proposing them. The problem will give you a proposed mechanism, and you have to say, is that valid or not? Okay? This says, studies of reaction mechanisms begin with the collection of data. Remember, rate laws are experimentally determined. So we will collect the data, and they will get a rate law. They will get the rate constant. They will get the orders of the reaction. You'll get all that stuff, right? You have that table of data. You'll figure all that stuff out. Then you actually have to figure out how could that reaction actually have occurred to get me that rate law. It says a plausible mechanism for the reaction can be suggested in terms of elementary steps. Plausible. This is scientists making their best guess to fit the actual data. And sometimes there are multiple different mechanisms that can work. And so how do we know what the correct one is? Well, it's just going to be more testing, other ways we can figure this stuff out. We can use those, remember us doing all that like IR spectroscopy and stuff? We can do some of that stuff to figure out what's actually in these things. So we can piece it together further, okay? So this isn't just people guessing, all right? But these steps have to satisfy two things in order for them to be plausible. If I add up all of the elementary steps, I have to get the actual overall balanced chemical equation. That has to happen. The other thing is whatever the slow step is, if it's first, second, or 18th step, it has to predict the same rate law as we got experimentally. Okay? So those two things have to occur. So let's look at an example. It says the decomposition of hydrogen peroxide is catalyzed by iodide ions. The overall reaction is 2 hydrogen peroxides decompose into 2 H2Os and an oxygen gas. By experiment, we found the rate law to be K, rate equals K, concentration of peroxide times concentration of iodide ions. Well, that means this reaction could not occur in one step. Because if it could occur in one step, the overall is the elementary. And if this was the elementary, the rate law would just be rate equals K times hydrogen peroxide squared. But it's not, which means there has to be multiple steps. So some scientists proposed this mechanism. Step 1, we take 1 peroxide with some iodide, and it breaks into these. Step 2, we take this intermediate, this IO negative, react it with the other peroxide, and it breaks into these. Now, here's the thing. You have to confirm, is the sum of the elementary steps the overall balanced equation? Okay. Well, there's a catalyst, it cancels out. All right. IO cancels out. It's an intermediate. What's left? On the left side, 2 H2O2s. Okay, that matches. On the right side, I have two H2Os, an O2, and that's it. Everything canceled out. So the overall reaction works. Well, if that's true, is the rate determining step, the slow step, step 1 or step 2? Okay. Pause the video and figure it out for yourself. All right, well, if you do that, well, the rate law says it has to be H2O2 to the first power times I to the first power. Well, if that's the case, step 1 has to be the slow step. Because if step 2 was the slow step, you would have two H2O2s, plus you would have an H2O that would have to be in there somehow. Okay? We don't know how to do that yet, because that didn't cancel out. So step 1 has to be slow. And that's it. Okay. So given the following elements, work this problem, okay, and watch Faribault, watch some of the daily videos, okay. Wish we were doing this together in class, but here we are. So, all right, that's all I got for you guys. I'll make another video for the next 2 topics, which would be Wednesday's lecture. Unfortunately, we're not going to get to do the relay race, but you'll live. So, all right, good luck and enjoy.